Hello, everybody. This is Doru Florescu with Park Systems. We are ready to begin. I just wanted to ensure that everybody had a chance to dial in and have a shareable version of our presentation on their screen. It is now time to start. So I wanted to give a quick introduction of this initiative that Park System is launching. We will host quarterly workshops in which we will be able to target most of the applications in the semiconductor space, storage space, based on our atomic force microscopes. For this first session, this is the kickoff session, we have a guest from Intel Corporation. It is my great pleasure to introduce Babar, which will be speaking after my presentation. So looking forward, please expect to see quarterly sessions in which we will have various speakers from the semiconductor industry or storage industry, hard disk drive industry joining us. And I hope you'll find this material useful. With that being said, let me begin by sharing my presentation with you. So the outline of today's talk is as follows. I will spend a little bit of time looking at the overall technology trends and some of the recent innovation that takes place in the semiconductor space. I will probably have 2 or 3 slides on the Park Systems AFM instrumentation to familiarize everybody with the tools that we offer. And then we will get into a few use cases using the automated AFMs that we manufacture. We'll look a little bit at some of the developments that we have in the pipeline. What is our roadmap and what is our thinking on getting more and more involved with these semiconductor applications, and we'll summarize the entire presentation. As we go through the presentation, we will leave 5 to 10 minutes at the end for Q&A. So please either raise your hand or make a note and bring your questions up at the end of our presentations for both myself and Babar. With that, let's look a little bit, again, I like to call this the 30,000-foot view of recent, and emerging trends that are happening around us. So we have, automotive development, self-driving cars, all the development that's happening in terms of electric vehicles, energy efficiency, healthcare, robotics progress, and then the Internet of Things. I assume everybody is familiar with at least some of these technology trends that are surrounding us on a day-to-day basis. And in order to enable these, in order to see how these are connected to the semiconductor market, you're looking at integrated circuits. So a lot of the parameters for integrated circuits are becoming tougher and tougher, more and more demanding, such as speed, efficiency, reliability, and even more. And then to start, integrating, networking, all the storage, all the applications, you need data transfer capability, you need analytics, you need massive storage and speed of transfer, which again is very, very critical. So these technologies, these emerging trends are really, really relying on continued semi-development. And with that, we note that the IC innovation is not slowing down. We've been guided by Moore's law for many, many years. We've seen a little bit of a slowdown in terms of Moore's law, but there are alternative techniques and alternative technological breakthroughs, such as some of the ones I mentioned here, which help us push the boundaries of development further and further, and the boundaries of performance further and further. And these are, things like DTCO, design technology co-optimization, and then the next step to system technology co-optimization. We have patterning advances, the EUV tools that are coming on the market. New structures, gate-all-around. I have a picture here of, the gate-all-around transistor. new materials, graphene. So there are a lot of advances and a lot of developments that are happening on getting nanodots or smaller and smaller and faster materials that are able to, you know, manufacture the transistors and the ICs and many others. So as we've seen, you know, the technologies that are driving the IC innovation is getting down to the IC itself to be driven as more performant, more efficient, and more cost effective. So a little bit about Park Systems. The company has been around for many years. We are a fully vertically integrated company in terms of atomic force microscopy. It is headquarters in South Korea. It's founded in 1997, and about 5 years ago we went IPO. They declared IPO. We actually have a picture here with our CEO on the Korean market. And ever since the IPO was declared, the revenue went up more than 2 times. Currently, we have about 250 employees worldwide, and you know, as you see, we have a global network of offices, 10 direct offices and many distributors. So depending on where your business is, you will probably find a Park Systems office nearby ready to support you. We have almost 2,000 tools installed, and you know, there's a ratio between, you know, R&D tools like tabletops and inline fully automated AFMs. There's more than 160 automated AFMs installed in various fabs, and we have 32 patents which have been published since 1997. In terms of technology, in terms of tools, as I mentioned, we have a full suite of AFMs. We have AFMs for research applications, you know, from very small tabletop to, you know, AFMs that come as standalone with enclosures. And then we have fully automated inline tools that can support, you know, 200, 300 millimeter 24/7 applications. Throughout our suite of tools, the technology, the core technology, is the basis, you know, the fundamental backbone to which we build these tools, and that is the decoupling of the XY from the Z motions. By doing that, we achieved advances in both XY movement, positioning, reproducibility, and Z sensitivity and capability to measure various features. And some examples are outlined below. So you can see things like atomic steps on a 1 micron scan. You can see E. coli, you can even see DNA. This image here shows a 1.5 micron scan of DNA. Switching over to more like inline applications, you can see nanotubes on a 2 micron scan. This is an image in which you're looking at a defect in an IC. This is a picture, a very high resolution picture. The scan size is 0.25 microns of a hard disk drive. And, you know, applications for litho, for instance. Somebody had fun here and made a couple of circles. But, you know, as mentioned previously, we are able to engage at various levels of research, development, and inline applications to support any of the use cases that our users demand. So let's go through a couple of use cases. As mentioned before, these are specifically designed and extracted from our semiconductor experience, and they can be applicable to any other industries in which you have a need, for instance here, the automated defect review use case. So what happens here? You have a bunch of DOIs, defects of interest, which, you know, show up in your processing, in your manufacturing line. And, you know, the process engineers are really keen on doing root cause analysis and, you know, troubleshooting any excursions or any departures from the normal process. For that, you need to know very precisely what is the size and what is the shape of these, and ideally, if you could, even more information about what these defects are. So our AFM solution is a very advantageous one. it's non-destructive. You can do non-destructive automatic defect review. It's a low in-fab cost, and through some of the ancillary modes that we offer, you may be able to take the defect nature investigation to the next level. You can do electrical measurements, magnetical measurements. You can do hardness and other options that I will probably cover in the next slides. So you have an optical inspection tool that can image your wafer. You transfer the wafer with a file to our AFM, and two examples here are given on a bump and a pit. This is our optical microscope view, and then you can locate the defect. You can do a large survey scan. In this case, I think it's about 10 microns, and then you can zoom in, and you can see a very nice bump here. You can measure, its height, its width. You do get an actual image of the bump. And then on the second example, there's a pit. So again, we can get the coordinates from the optical inspection tool, navigate to those coordinates, find the defect in our optical microscope, do a survey scan, and then zoom in, and you get absolute clear imaging of this pit in terms of size, shape, and so forth. Moving to the next example, this refers to wafer edge. So as I mentioned, our tools are fully automated for 200 and 300 millimeter wafers. And as we see, the process edge exclusion, which ranges from anywhere between 1.5 to 3.5 or even 5 millimeters wide, is becoming smaller and smaller. The reason for that is that manufacturers want to increase the real estate that they have on the wafer, and in order to do that, you have to be able to look at both the wafer edge and the process layers that are being deposited closer and closer to the edge. So again, what is the AFM solution that we offer? Is a non-destructive review, again, low in-fab cost, and not only looking at the AFM scans. The typical AFM scans can be all the way up to 100 by 100 microns. You can enable additional options through some of the offerings we have with our technology. One of them being the long-range profiler. So two examples here. These are just wafers that can be run in our tools, and you can see the optical microscope image. And then you see that you have a silicon dioxide film, you have the wafer, and then that's the wafer edge. You can do a top view, you can do a 3D view, and get accurate metrology and inspection on various regions of both the silicon substrate and the film that was deposited on it. That's for unpatterned wafers applications. You can expand this even to pattern wafers. An example is shown below, in which we have a long-range profiler that actually scanned across. These long-range profiling scans go in the size of millimeters, and you can see that you can very clearly resolve the pattern and the wafer edge shape. So going back to the ROI of your investment is very, very non-destructive way the wafer can be further used. We have a very good footprint for fabs, so the in-fab cost is kept to a very attractive number. So what are we doing next? Well, we're looking at expanding and getting more footprint on fab applications, and we're doing that by looking at new modes. We're doing that by looking and developing new tools and new partnerships. So examples of each. One of the modes that is being released this year is called narrow trench mode. And this mode, I think I have an animation here. Yes, it's based on one of our technologies, Pinpoint, and enables scans of very high aspect ratios. And I have an example of various probes. Of course, the way you scan these very, very narrow trenches, as a combination of your scan capability and the probe you use. So using various probes and customizing these probes for our scan, we can see that trenches that before were sort of invisible, of widths of 11 nanometers, are now being imaged. The tool that I wanted to mention in terms of new tool release, which also happened this year, is the tip scanning head tool, TSH. And this tool, you know, we went with our standard technology, but integrated it into the tip, into the head of the AFM, enabling the ability to scan large samples. So we have samples that, you know, can go all the way to about, you know, 0.5 meter by 0.5 meter, very thick, very heavy. And, you know, applications for these, you know, come to mind could be, you know, optical displays, back-end applications. So these large samples can be mounted and can be handled. And then with the tip scanning head technology, we're able to generate the same high quality and state-of-the-art imaging that we generate with any of our AFMs. And in terms of partnership, we recently announced, this is again just one example, that we recently announced an equity investment in a company called Molecular Vista. They have a very, very impressive photo-induced force microscopy module, which we're looking forward to integrating you know, on our tools. Preliminary results are very encouraging, and this takes us to what I mentioned earlier, the capability of not only imaging some of these defects, but conducting advanced investigation or advanced measurements on these defects, such as, you know, chemical, infrared analysis, you know, material composition, which are critical to taking the next step into the IC development and manufacturing. So that brings me to my summary. We see that, you know, overall in today's world, we have a lot of emerging technologies, and these are very, very rapid trends given by the fact that, you know, more communication is needed, more exchange of information is needed for things like automotive, Internet of Things. And these technologies are driving very, very sustained innovation and growth in the semiconductor, storage, and hard disk drive industries. Our company offers fully automated fleet matching AFM tools, which are proven and, you know, facilitate day-to-day solutions for, you know, troubleshooting or controlling any manufacturing yields. We have a lot of experience with a lot of use cases in the field, and we hope that, you know, any use case that seems impossible, you bring it to our attention and we can devise a solution for it. And we're not limiting ourselves to just what we're doing today. We're always looking forward. So developing new modes, developing new tools for even more challenging applications, and doing, you know, a lot of partnership. As I mentioned before, with Molecular Vista, we have another ongoing partnership with IMEC in Europe, which is very, very fruitful. We believe that these modes and the ability to go at the nano scale will be key to overcoming any design and manufacturing challenges that occur in driving the technologies. With that, I would like to thank you for your attention. I have a tendency to go a little fast on my slides, but you know, as mentioned when I opened, we have some time for questions, and I would like to open it up for any questions that you may have at this time. If none at this time, I encourage you to follow up with us. I'll be more than happy to follow up with anybody after this meeting. So if no questions at this time, I would like to switch my presentation to our guest speaker, which, as I mentioned before, is Babar from Intel.
All right, thank you so much for this opportunity. I'm really glad to work with Park on the AFM tool we have, and we are working on some development activities. And at the same time, we provide feedback to Park, and they entertain our requirements. And it's a really good attitude that we see in this company, that they're always open to try new things and accept challenges. All right, so I'm here to present like few challenges we are having in measurements, and maybe suggest a couple of things, and we will continue this discussion in future. Uh, uh, Doru has already introduced me. My name is Babar Hussain. I'm a process engineer at Intel. I've been working on many different tools, but specifically a few AFM tools from different companies. And I started working on AFM from Park in last few months, which is a nice experience. So what we are trying to do right now is developing some processes in silicon photonics and memory side, and that we call NSG, solutions, non-volatile memory solutions group. There, during development, we need to get TEMs and SEMs at almost every step of the process. And in current scenario, we have like turnaround time of this TEM in weeks, sometimes like 2 weeks or more than that, which is uh, which is a main bottleneck in the development process. And we are trying to substitute AFM with many measurements. And I think that we can do more than what we are doing right now. So AFM is definitely slower than optical measurements, but it is non-destructive, and it is definitely faster than TEM and SEM. Um, so I will go to the next slide and give an example of measuring specific structures using AFM. So what we are doing right now, we are trying to optimize what we call spacers. You can see my mouse cursor, right?
Yes, Babar.
Okay. So here's a structure, like there are few different materials. This is silicon, and then oxide, and then some polysilicon, and then nitride. So these are very critical dimensions for us, like this spacer width, because it defines area of implantation underneath. So you can measure this structure by optical tools like spectrometry, but that is not very reliable measurement. And additionally, it usually measures on repeated structures, right? For spectrometry, you need a repeated structure, several pitches, or like at least few microns structure. In silicon photonics, we don't have a lot of repeated structure. In logic, in memory, we do have, and that works. But in silicon photonics, most of time we have just one structure, and we are interested in measuring weights and spacer thicknesses. For that, we have no option but TEM and SEM, and as I said, we have to sacrifice our wafer, and then the turnaround time is very long depending on the priorities. Even if it is a high priority, we don't get results before a couple of days or so. So what we were trying, using our AFM tool that Park has provided, so we will just measure the profile on the top. There are a few different materials, especially we are interested in measuring these dimensions. This is nitride, the width, and this thickness. So uh, if we assume that wherever this slope starts, that is, this material starts from that point, because we cannot tell, right? It's just a single line. So if we assume that, then it can give us some idea of this thickness from this point to that point. But usually we are interested in this thickness and this thickness, so it's hard to tell this way. But if we can do two additions, like one tip deconvolution, which is already part of this system, but we are not sure it's working. The reason is that we have measured some known structures, and we were expecting some different than what we are getting. And the solution for that would be, a simple solution would be, it's picture I have copied from this paper, and it's a very nice detailed paper of tip deconvolution. There are so many variables: this angle, front angle, back angle, and there are some other angles. When this tip moves to the side wall, then this tends to tilt this way in the left side, and that's another additional angle. So we have to take care of all of that, and I'm sure folks from Park know much better than me about that. But what I would say, what I would suggest is to make our customers believe that it is working and what we are making exactly true, is that definitely there is a reference structure on the tool that the tool uses to scan and then find the shape of the tip and then apply that information on the measurement structure and get the and do the tip deconvolution and get the real values of the structure width especially. Like structure height is not an issue in this case. If we are trying to measure roughness on the top, that's not the issue in this case. But if we are trying to measure width of this structure, that can be an issue if tip deconvolution is not working. And what we want to see is like if we can use the reference structure on the tool that you use for tip deconvolution. Once you measure that structure, you apply tip deconvolution, you go back to that structure and then provide us or provide your customers these values, like what is the top width, what is the middle one, what's the bottom one, what is the targets, and what are the measurement ones. And definitely if you can show some picture like TEM of the same structure that you have installed on your tool, that this is the real structure and this is what we are measuring right now, that will help a lot. Otherwise it's always very confusing because tip always wears off. There are so many different applications, there are so many different tips. So that's one of the suggestions. Another idea is, and I'm sure you're already doing this, as Doru mentioned in his presentation, that AFM can do much more than measuring heights and widths. It can measure electrical properties, it can measure mechanical properties. So, and you don't have to make a lot of changes in the tool for that, right? I know there are some AFM tools that combine optical measurements and AFM measurements, but that's a big change. But even on existing tool, if we can use if we can measure material properties while scanning and then color code it, for example, the application or the example I mentioned, if we are trying to measure this width and this thickness along x-axis and y-axis, so if I've just drew these colored lines myself on the top of this as an example, if our tip is scanning and there are x, y, z variables already the tool knows, but if there's a fourth variable which is, let's say, material property, let's say hardness or dielectric or constant or whatever, so if we can color code this line, it will help a lot, right? So if we know that this material is starting exactly from this point and ending at this point, and if you look at the x projection, it will give us exactly the width of this spacer. So it is going to save us huge amount of time if we can do it with AFM instead of sending our wafers to the cross section cut, and we don't have to sacrifice our wafers too. This is inline measurement. That would be great. Similarly, on this part of the curve, this blue part of the curve, if you look at the y projection, this will give us this thickness. So I don't know if currently you have made it an option in the tool, but the one we have, as far as I know, we don't have this option, but this would be a great addition, I would say, and it will expand the scope of this tool a lot, not only for us but definitely for your other customers too. Another idea which I've already presented to Park, and we are already using this, we don't have it a part of the tool analysis, but we are doing it in our own analysis like MATLAB or Python. So this is a very nice and interesting application, both in silicon photonics and memory, that a lot of times we want a structure to be rounded or to be squared depending on the application. So for that we need to measure and we need to analyze, preferably inline, that what is the roundness of the structure. In this specific application, the picture I'm showing, our interest is to make the structure rounded, more rounded, because it affects, number one, it affects this thickness of oxide. This is silicon. On top of it, this is oxide, and it affects the thickness of the oxide in the corner, which is definitely different than the thickness you can see on the top. So this thinning is somehow related to the geometry of the structure, and if we believe if we can make it more rounded, then this effect will reduce, so we can increase this thickness at this corner. So one of the main issues in process. So what we are doing is, and another example where we would need a very square structure is just contacts. The trenches, we need them to be very square, not rounded. So there are some analysis available on the tool, but they are mostly like just overall squareness, not an individual corner of the structure. And it doesn't work all the time, because probably it's for very specific application, like if the structure is like very round all the way, like a circle, because this is ROC, radius of curvature, and it applies only on the square, on the curved or circular structures. So what we are doing, we are capturing this image, and I'm really glad that I'm getting these scans from Park FM tool. We are getting very less noise, very high signal to noise ratio, and very smooth structures and very quick measurements. But when we capture this data, we just capture the raw data file, and then in our algorithm, we're just drawing a virtual line like this. This is not like just a virtual line anywhere on this structure. This line is intersecting this curve at multiple points, and we are interested in this wider structure, measuring corner roundness on this wider structure. So depending on these intersection points and looking at the distances between those, we decide which structure is the right one to measure, right? This is a benefit. I would say this is a good way to find it, because if we try to measure it based on the position, like if we have a scan and if we say we are trying to get a structure from 240 to let's say 350 or 400, between 400, and if this scan starts from somewhere here instead of here, every time it can be different, so we can detect a different structure. So this way we can definitely pick the right structure to measure. And depending on the width of the structures, you can see there are three different widths, 1, 2, and 3. So we can give a range, like if the width is from less than and greater than this value, then that's the structure, and you can pick all those structures and then apply the algorithm on that. So what we are doing, instead of radius of curvature, we define our own roundness metric, which is basically simply this formula. So for that, we already know these points. So on these intersection points, so based on these 2 points and based on the peak of this structure, we can draw a bigger rectangle and then divide it into 2, so we can find individual corner roundnesses. So the integrate this curve within that, this blue curve, simple integrate, numerically integrate that. This will give you area under this blue curve, and divided by the area of this red box, this part of the equation, area under the curve divided by area of the box. So this value will give you a standard for squareness, right? Like if this value is higher, this structure is more square. The maximum value will be 1 if this curve area is equal to this box area. So this value will be 1, and roundness will be 0 in that case. So then subtract it from 1, and to represent it in percentages, multiply it with 100, and we call it roundness. So this is, in our experience, is a very good way and very robust way, because if the structure is not perfectly round in the corner, so how do you draw a circle and look at the radius of curvature? So for example, look at this structure. So where is the radius of curvature? Is this circle, or is this whole thing? So I would say this is more robust way and dynamic way of calculating the roundness in the corner, and so many applications in industry. So if we can make this part of our tool analysis, that would be a good change. I have already mentioned these advantages of this corner roundness measurement, and I think I have worked with Park, and we have provided them algorithm and everything to make it part of the tool analysis. So we can already measure these roundness in line, but what we have to do, analysis. We have to do offline analysis, and we cannot post our data to the charts, to our automation charts. So if it can become part of the tool analysis, then will be much easier for us to publish this data in our chart so everyone can see, including our customers. That's all I had. Thank you for your patience, and if any questions.
Thank you, Babar. This is Doru. Really appreciate the feedback and the collaboration that and guidance that we're receiving. As mentioned, we're expanding our options, we're expanding our tools, and we're expanding our partnerships in order to solve more and more puzzles that help drive the semiconductor industry and others. So really appreciate you presenting, and really appreciate the feedback and the utilization of the tool. And everybody, as Babar mentioned, we're open for questions. Please either raise your hand or if any questions or follow-ups, we'll be happy to do those as well offline.
Sure, you can send me emails too if you want.
So we have one hand raised, Lee.
Yeah, I'm a undergraduate student at the University of Illinois. Thank you so much for having a great webinar today. My question is to Mr. Babar.
Yes, please.
So I believe it's second or third slide of yours that you showed you're using AFM to scan the specific images that used to was done by TM or SEM, like actually it's before this.
This one?
Yeah, it's before this. Yeah, this part. So I want to ask, do we assume the substrate is held or fixed there? We cannot like tilt it or rotate it in some ways?
Yeah, that's a good question. That's usually made part of the tool analysis. Like tilt in the image can be due to the stage tilt, it can be due to the tilt in the wafer, it can be due to the bow in the wafer. So yeah, so I think tool takes care of that part. It takes really good care of that. Usually the raw images we get are usually tilted. They are not perfectly horizontal, and yeah, and they fix that, and after fixing the tilt, then we apply other algorithms.
That makes sense. Thank you so much.
Did I answer your question? Yeah, here basically I was showing, what I was trying to show is there are so many other issues we are dealing with. That is an issue, but not a big issue, because it's very good. Most of the tools are very good at minusing that effect of tilt or bow or in the substrate. But what we are seeing is, if you can see, right, this is the real structure. This black line is the real structure, and this blue is the scanned curve using this tip, because tip is not an ideal tip, right? It's a physical tip. It's like a pyramid, and when it scans, so it gives you scan across according to the movement of this tip, and this tip is moving this way on the blue curve. So what we get is this structure. And most of people, and there are so many papers, you can go and see tip deconvolution. There's very nice techniques to just minus this effect. What you need to know is, this is a known structure. If you assume this is a known structure that you know really well, plus minus 1% or something, you have a TEM of that, and you know what exactly this is. So if you move your tip on that, so you know the actual structure size, and when you get the measured ones, you can subtract those effects from a measurement structure, right? The structure here I'm showing is just an example. It's just a schematic of of a known structure. So once you measure that, I've measured that, and now I know how much, for example, I know how much this angle is, or how much this angle is, and this small angle in the white area, and then I can write like this structure. Measured structure is not exactly the real one. This is that blue curve. This blue curve here. Sorry, this blue curve. So now I apply that knowledge from the known structure, and then get the real structure from the raw scan. That's the challenge. That's a challenge. In my experience, it is part of most advanced tools, AFM tools. But when we look at numbers, when we look at TEMs, it doesn't work many times. Many times it doesn't work. So it actually affects the value of this tool and raises question on the reliability. So if we can solve this, what I was suggesting is if we can apply provide these values every time we do such a measurement, that this is the measured value and this is the target value of the reference structure. And if these values are very close, that would be a good addition. So we were trying to measure this, and actually it was helping us a lot. One of the example is it still helped us. It still helped saved us like weeks of time, because I intentionally put this scan here is because this is nitride, right? This is this structure. These are not same, these are different ones, but I put just an example. So here in the TEM, this structure is pretty nice. The nitride curve is pretty nice, but here you can see a dip. When we got the TEM of this, we actually saw that dip, and it was actually overetching this nitride, which was undesired. And until they had resolved this issue, we were using AFM for that, and it was saving us tremendous amount of time because we didn't have to send for just to look at that dip. We didn't have to send it for TEM, right? So still helps us. But for example, I was saying, if for example, if we actually are interested in measuring this width too, it defines the implantation under this area or under this area, especially this thickness and this width, this whole width. That is possible only if we apply this tip deconvolution perfectly, right? And additionally, if we can do color coded based on the material properties, that will be a plus. So this is a sort of suggestion, like we can make it part of our tool analysis based on the material properties, and people would love to see such scans, and they will trust this tool measurements much more than they are doing now. So this way we can substitute TEM and SEM in at least some specific measurements and can save a lot of time. And I've mentioned that time is money.
Yep, great discussion. And these are the type of challenges that we as equipment manufacturer are looking at. And the tool at Intel, as I mentioned before, we have a new mode coming up on narrow trenching where the probes are critical. There are new probes which are even sharper and high aspect ratio to be able to resolve more of the sidewalls and sidewall roughness. We have tools that tilt their head to actually be able to do more measurements, even undercut measurements on 3D structures. So we need to push and push the technology on the existing platforms that we have by combining, BKMs and probes and ways of measuring and adding additional modes, which is exactly what Babar is mentioning. Great discussion. Thank you.
Thank you. Any other questions? You can follow up with emails as well. I'm always open.
Yeah, so you guys will receive attendees will receive a notification after that. We will include our contacts. So both for me and Babar, please feel free to follow up with us. And if any of your colleagues or any peers, come across some of these topics, please connect them through us. We would like to help. So 45 minutes, I believe that concludes our first session. I wanted to thank everybody involved. Thank Babar again and Intel for being a partner for us, a customer and a partner. Thank you guys for joining. We will receive advanced notification of the next session. It will happen next quarter. We plan to have this on a quarterly basis. Please help spread the word and help you know, give us as many challenges as you can find. We love those. And with that, I think we are done. Thanks again for calling in today, and I appreciate your time.
Thank you so much.